Now we're going to look at our data and analyze it a bit. Now, if you did this activity on your own, if you constructed your own ramp, ran your own balls, you'll have your own data, so your graph might not look exactly like this. But you can apply what we're going to do here to your own graph. The idea is the same. We're mostly going to talk about Galileo's results and then compare those to our results. So first, let's talk about Galileo's results. He found that, to his surprise, when he ran balls down his ramp, he noticed that if he divided the ramp into 4 sections, he took the total length divided by 4, he discovered that the time it took to go from the starting point to the first mark at 1/4 the length, let's say this is 1 second, it would take that same amount of time to cover the entire remaining 3/4 of the ramp. So if this took 1 second, this would take 1 second. This is very surprising. How could it cover 3/4 of the ramp in the same time that it took to do 1/4 of the ramp? So let's see if we can find this pattern in our data. You can see I've copied this over to make it a little bit neater and put some exact figures in for us. So let's divide our total time, which is about 8 seconds. Let's look at this, the shallower graph first, this one. Our total time was about 8 seconds, and half of that is 4 seconds. So that means that in these equal time periods, 4 seconds and then 4 seconds, in the first 4 seconds, it should travel 1/4 of what it does in the 8 seconds. Okay, so let's see. Let's go up from 4 seconds, and it hits the line a little under 5. So that means that the remaining 3/4 should be 5 times 3 is 15, right? The 20-foot ramp would be 5 feet in the first quarter and then 15 feet. So let's see, it has to go 15 feet between 4 and 8 seconds. So that means it should end up at the 20 at 8, the 8 mark. And we go all the way up, and where does it bump in? Sure enough, right about the 20. Okay, do you see that? In 4 seconds, it went 5 feet, and in 8 seconds, it went 20 feet. Now, what about our other line for the steeper ramp? Well, we don't have 8 seconds. We can do it with 6. See, we don't even have a dot for 7. So let's use 6. Let's go straight up from 6 seconds. And it hits right here, right about the 16. If I draw a line over, this is 16. Right there. So see how 6 and 16 meet right there. Okay, so we have 16 feet. So that means in half of that time, in 3 seconds, let's see, 16 divided by 4 is 4. So it should go 4 feet in 3 seconds, does it? Here's the 3, and we go up to the 4. Okay, close, close. It looks like it crosses at like 4 point something, a little under 5, but it's close. Okay, so we were in the ballpark there with both of them. So now let's look at Galileo's odd number rule and see if our data corresponds to that rule. So Galileo found that if something traveled a certain distance in 1 second, we'll put our time down here, then in the next second, it would travel 3 times that much, which is kind of what we just said, right? The ratio here would be 1 to 3. It would be 3 units, right? And then in the next second, at the 3 second mark, it travels 5 more because it was accelerating. So this is 5 of our original units. And then the next second it travels 7 of those original units. And then in the next second, this will be the 5-second mark, it would have traveled 9 of those original units. And then in the next second, it traveled 11 of those units, the 6-second mark. So no matter what those units are, we could say these were inches. 1 inch, 3 inches, 5 inches, 7 inches. We could call them meters. It doesn't matter, but everything is based on that original unit at the 1 second mark. So to analyze our data, we're going to find out how far the ball traveled after 1 second. Now this is a little bit difficult. This is really small down here, so I kind of increased the size a bit so we can see. If we could zoom in, this is a zoom in on this little corner right here. Now we know that 0, 0 is a data point because if I put our ball at the 0 mark, it would take 0 seconds, right? So we know that's a dot. But then we didn't have any measure, like we didn't do half a foot. I should have done half a foot. So we have this blank place, and I just drew it in down here. But actually what we're doing here is extrapolation. We don't have any data, so we're going to have to extrapolate. And that means to take a good guess by drawing your curve. So if the curve kind of comes down like this, we sort of kind of continue the curve best we can. We imagine if the curve were here, what would the curve have to look like down here to match its shape up here? So we'll just kind of go like this. Assuming that everything keeps behaving the way it was, we would get something like this. Alright, so now we can look at the 1 second mark. So if we go up from here, this is 1 foot, this would be 1, 2, 3, 4, so half of this would be the 6-inch mark, and this would be 3-inch mark. So it looks like we're about at the 4-inch mark. So we can't be sure exact. 4.5, definitely less than 6, definitely more than 3. So I actually ran some numbers. I took a couple hours running the numbers on what would work for this, and it looks like 4 is maybe our best shot if this hits right at the 4-inch mark. And sorry for everybody that isn't used to the English system. This isn't metric. But anyways, it'll be interesting to see how things work in feet and inches if you're not used to that. Okay, so let's say that in 1 second it hits at 4 inches for this line. Okay, let's go with that. And then if we work this out with the odd numbers rule, that means that our unit here would be 4 inches. Right? That's our starting unit. So 3 of those 4-inch units, 3 times 4 is 12, so this will be 12 inches. Then 5 of those, 5 times 4 would be 20 inches. 7 times 4 would be 28 inches. 9 times 4 would be 36 inches. 11 times 4 would be 44 inches. So then what we'd need to do would be to add these together to get where it should be at the 2-second mark. So we have 4 inches plus 12 inches equals 16 inches. So if it's at the 4-inch mark here, it should be at the 16. After 2 seconds, it should be at the 16-inch mark. And 16 inches is 1 foot and 4 inches. So we use this little 1 hash mark for a foot and then 2 hash marks for inches, just in case you're not used to the system. So we have then we add 20 inches, so 16 and 20 would be 36 inches. 36 inches happens to be exactly 3 feet, so that'll be easy to graph. Then we add another 28 inches to that, and we get 64 inches, which is 5 feet 4 inches. And then we add 36 inches to that to get 100 inches, which is 8 feet 4 inches. And then we add 44 inches to get 144 inches, which is 12 feet. So, will this correspond to our graph? Let's see. At 1 second, we have 4 inches. That will be our point down here. At 2 seconds, I should hit at the 1 foot 4 inch mark. So we go up 2 seconds, and you can see it's about, yeah, it is about 1. I can believe that 1 foot. It's a little over the 1 mark here. And at 3 seconds, we have 3 feet. 3 seconds, we should hit at 3 feet. It just about does. At 4 seconds, we should hit at the 5 foot mark. 4 seconds, we go up, yeah, right about here. It's not exact. It's a little bit low, but it's in the ballpark. At the 5 second mark, we should hit at 8 feet, a little over 8. So let's go up in here. Where do we hit? We trace over here. Okay, we're a little low on that one. This should be up here. We're a little bit low on that. What about at the 6 second mark? 12. So if we go straight up, it hits. So here's where it goes off. It's only at the 9. So it should be kind of up here. So our dots, it looks like Galileo's line is going to go up a little bit steeper like that. So then if this were a really important experiment that we had to really figure out, we'd have to determine why our results were different from the predicted, and we'd have to look at the ramp, go back and see were there any low spots in the ramp, where the ball ran a little too fast or slow, or, you know, we'd have to go back over our techniques. So we'd have to do this experiment again and again. Galileo did this experiment for hours, days, weeks, months on end. It may have taken him a couple years to come to his final conclusion. He spent a lot of time rolling these balls down. And if he didn't like the results, like, he would then take sandpaper probably and smooth the track. We know that he spent a lot of time perfecting the track, making sure the ball was perfectly round. The track was really, really, really smooth. So he knew that that was really important, to have everything perfectly square, perfectly smooth, perfectly round in order to get accurate results. So my track wasn't perfect. If you did it yourself, I'm sure your track probably wasn't perfect. So overall, I'm pretty happy with the results. We at least confirmed this, where we did the 4 and the 8 and the 3 and the 6. That worked pretty well. So in that regard, our experiment was a success.